In this tutorial, we will be discussing the applications of redox. Electroplating is a form of electrolysis. In electroplating, the workpiece is the cathode. Cations are reduced at the cathode to plate the surface of the workpiece. The anode is made of plate metal. The anode oxidizes and replaces the metal cations in the solution. Consider the electrolysis of aqueous silver ion. It will take 1 mole of electrons to produce 1 mole of silver. By knowing the moles of electrons required to make the pure metal silver from its ion silver plus, the amount of pure metal silver can be determined quantitatively. If we take Faraday's law, the amount of metal deposited during the electrolysis is directly proportional to the charge of the metal's cation, the current, and the length of time of the process, because charge is equal to current times time, where current is defined as the charge per time. The charge is in coulombs, and the time is in seconds. Coulombs per second is also known as amperes. To relate the moles of electrons to the current, we use Faraday's constant, which is 96,458 coulombs per mole. So let's use this information in a practice problem. If we have 1.50 amps flow through silver ion solution for 15 minutes, determine the mass of the silver metal deposited. First thing you need to know is to determine the charge. Remember, the charge is current times time. So we know that we have 1.50 amps times the time, but it needs to be in seconds, and we have it in minutes. So 15 minutes, and every minute there's 60 seconds, and that comes out to be 900 seconds. Multiply that through, and it comes out to be 1,350 coulombs. From here, we can calculate the moles of electrons needed by taking the charge, that 1,350 coulombs, times the number of moles transferred, number of moles of electrons transferred, since it's going from a positive 1 to 0, is going to be 1. And then Faraday's constant is 96,458. That comes out to be 0.0140 moles of moles. From here we can determine the mass of silver that we need for that. So if we know we have 0.0140 moles of electrons, for every 1 mole of electrons, we need 1 mole of silver. And for every 1 mole of silver, we need 108 grams per mole. And we got that from the periodic table. Multiply that out, and it comes out to be 1.51 grams. For the remainder of this video, we're going to talk about applications such as batteries and plating of metals to prevent corrosion. In batteries, you have an electrolyte that's a paste and an anode and cathode that are solids. In an acidic dry cell, you have zinc with ammonium chloride or magnesium bromide, where the anode is either the zinc or magnesium, and the cathode is a graphite rod where manganese oxide is reduced. And this has a cell voltage of 1.5 volts. However, these are expensive, non-rechargeable, heavy, and very corrosive. However, we do have alkaline dry cell batteries, which are more commonly sold. It has the same basic cell design as the acidic dry cell, except the electrolyte is a potassium hydroxide paste. You'll notice that the potassium hydroxide comes up a lot in these these batteries. Its anode, once again, is either zinc or magnesium, and you're still reducing the magnesium oxide. So here's the terminal, and around it, here's the graphite rod. Around it we have this moist paste, and that's what you'll see seeping out of a battery if it's been sitting around too long. And then the zinc is along the outside of it, and then the negative terminal is on the bottom. This has a cell voltage of 1.54 volts. Commercially, it has a longer shelf life than the acidic dry cells. It is rechargeable with little corrosion of zinc anode. The lead storage batteries, which is what you'll find in cars, has 6 cells in series. The electrolyte is 30% sulfuric acid. Where the anode is lead, there's lead plates in here. And the cathode is lead coated with lead oxide. Then the lead oxide is reduced. It has a cell voltage of 2.09 volts. It is rechargeable and very, very heavy. It uses redox reactions that can be reversed, which is why you're hooked up in the car to make it recharge. Nickel, cadmium, or nickel metal batteries, once again, have that KOH solution, except now is a concentrated solution rather than a paste. The anode is cadmium, or a meta-alloy with a dissolved hydrogen. The cathode is nickel coated with nickel oxide, where nickel oxide is reduced. It has a voltage of 1.30 volts. It's rechargeable, long life, and lightweight. However, recharging incorrectly can lead to the battery breakdown. This is the predecessor to the lithium ion battery, which is what you typically use when you see computers or smartphones and things like that. Once again, you have the KOH solution. The anode is the graphite of lithium ions. The cathode is a lithium with a transition metal oxide compound, the reduction of the transition metal. These are rechargeable, long life, very light, more environmentally friendly, and greater energy density. Now, the backdrop of the redox reaction is corrosion. Corrosion is the spontaneous oxidation of a metal by chemicals in the environment. Since many materials used in everyday life are active metals, corrosion can be a very big problem. Rusting, for instance, is the hydration of the iron 3 oxide. To have rusting, you must have moisture in the area, because water is one of the reactants. It is required for flow between the cathode and the anode. Electrolytes promote rusting because they enhance the current flow. Also, the lower the pH, the lower the cell potential, and that promotes the rusting as well. So here's an illustration of what's happening. We have pure iron. When it becomes oxidized and then mixes with the water and the air, you get this complex here of iron hydrate, and that's the red color you'll see. To prevent it, we can coat it with zinc, and that's what they mean by galvanized. And then the zinc becomes oxidized rather than the iron. One way to reduce or slow corrosion is to coat the metal surface to keep it from contacting corrosive chemicals in the environment, such as painting it, or coating it with another metal, like aluminum or zinc, to form an oxide that strongly attaches to the metal surface, preventing the rest from corroding. Another metal is to protect one metal is to attach it to a more reactive metal that is cheap, such as the zinc. It's considered a sacrificial electrode, in, for instance, the galvanized nails. Alright, and that is different applications of redox.